Hello, good evening. Am I audible? Am I audible? Yes, please put in the chat box. Am I audible? Let me check. Yes. Yes, am I audible? Yes, just a second. Yes, am I audible? Yes. Okay, let's start the session. Good evening, one and all. Welcome to Goscore Learning. We are the fastest growing EdTech in GCC. Our aim is to provide education for all. Okay, so today this is the fifth chapter of grade 12 physics, magnetism and matter, and this is the second part. Okay, so grade 12 physics, fifth chapter, magnetism and matter. And in our channel, if you check it up, means you can see the first part also, magnetism and matter. This is a very small chapter in grade 12 physics. Okay, so we can directly move into the chapter. If you are having any doubts in the first portion I have taken, please put in the chat box. Okay, anyway, let's start. Okay, so in the last class, we have discussed torque on a dipole, magnetic dipole placed in a magnetic field. And here, today's first topic is current loop as a magnetic dipole. So, in the previous chapter, chapter 4, moving charges and magnetism, we have seen that a current loop, current carrying conductor, current loop will act as a magnetic dipole. Okay, so we have a derivation related to that topic in the previous chapter, and today I'll be giving you a trick to remember. So once the current loop is behave as a magnet, definitely there will be north and south pole, right? So let us check how will be the north and south pole is formed in a current carrying loop. Okay, so here I have drawn two loops in which current in the first loop is gone in anti-clockwise direction, right? So the same loop, if you are looking from the back side, you can see that when we looking from the back side, we'll be see that current is in the clockwise direction. Okay, so once we are looking from here, we can see that current in the anti-clockwise direction, and same loop once we look up in the other side, we'll be see that it is in the clockwise direction. So there will be reversal. That is understood, right? Okay, so for a current carrying loop, carrying current in the anti-clockwise direction. Okay, so current carrying loop and carrying current in the anti-clockwise direction. So this is anti-clockwise, right? So anti-clockwise direction will produce a magnetic north pole. So this is N, right? So current loop and having current in the anti-clockwise direction. Anti-clockwise direction will behaves like a magnetic north pole. Will behaves like a magnetic north pole. So this is a trick how you can remember. Anti-clockwise, please write a N in the middle and it will be shown like it is in the anti-clockwise direction. Okay, so when the current is in clockwise direction, so as here it is given, current in the clockwise direction. Okay, current in the clockwise direction, and it is giving a magnetic south pole. So we can write N here and write S here. This is look like an S, right? So current carrying conductor, current in the clockwise direction, current carrying loop, current in the clockwise direction. It is a magnetic south pole, and current carrying conductor, current in the anti-clockwise direction behaves like a magnetic north pole, and this rule is known as clock rule. Okay, so this is a trick you can remember. Anti-clockwise direction, the magnetic loop will be the current loop will be magnetic north pole, and clockwise current will give rise to a magnetic south pole. Actually, if you are looking from this side, this is north pole. On the other side, if you are looking from the back side, we'll see that current is in the clockwise direction. It's dependable, right? We depend on the position and in which position we are looking at. So on the other side, it will be a magnetic south pole. Whenever there is a north pole, definitely there should be a south pole. Magnetic monopole do not exist. Always magnetic poles are exist in pairs, that we have discussed in the last class. Okay, is it easy? Is this easy? Okay, so remember this rule in the next chapter. What is the name of our next chapter? Upcoming chapter is electromagnetic induction. So in electromagnetic induction chapter, this trick will help us to find for the application of Lenz's loop. Okay, so remember this trick while I am taking the class for that topic. Okay, so next one of the last topic of this chapter. When a current is passed through a solenoid, it will behave like a bar magnet. When a current is passing through a solenoid, it is behave like a bar magnet. Let's see what are the similarities or resemblance with bar magnet. Okay, so you are familiar with bar magnet, right? So this is, imagine this as a bar magnet, north pole and south pole. So how will be the magnetic field lines of a bar magnet look like? It will be like this. Okay, starting from north pole and in south pole. Sorry, starting from north pole ends in south pole. Starting from north pole ends in south pole. Right. Starting from north pole ends in south pole. Yes. So this will be the magnetic field lines, representation of magnetic field lines of a bar magnet, right? Of a bar magnet, it will be like this. Okay, it will be like this. Okay, now just see the magnetic field formed by a solenoid. We have seen how, we have explained how a solenoid form this kind of magnetic field lines in the previous chapter. Okay, so look at the resemblance of magnetic field lines of a bar magnet and a solenoid. So the magnetic field lines of holes have very much resemblance with the solenoid and a bar magnet. And not only that, so what happen if you are freely hanging a bar magnet? It will align in the north-south direction, right? It will align in the north-south direction. Okay, for here also, if you are freely hanging or freely suspended a current carrying solenoid, definitely it also align in the north-south direction. Okay, so what happen if you are taken a 2-bar magnet and if you are keeping the north side of 2-bar magnet together, what happen? Like poles will repel, right? Like pole will definitely repel. Also, if you are for here, this will be the, just a second. Okay, this will be the north pole of the solenoid and south pole of the solenoid as a magnetism. Okay, so this is the position in which magnetic field lines are arises. So definitely it will be a north pole and this will be a south pole. Okay, so if you are having two north pole of if you are having a pair of solenoid carrying current, then once we are keeping this north pole together, what happens? They will repel like a bar magnet. Two north pole of a bar magnet will repel, right? If you have taken 2 bar magnet and when we keep the 2 north pole together, they will repel. So similarly, the solenoid is also showing that kind of phenomenon. Also, what happen if south pole of another bar magnet and north pole of a bar magnet keeping together, they will attract. Unlike poles attract. Same phenomena you can observe here. So these are some resemblance with a current carrying solenoid and a bar magnet. Okay. So then the important thing is a bar magnet as an equivalent solenoid. How is, we have seen that the magnetic field lines of a bar magnet and a solenoid have huge resemblance. Similarly, how a bar magnet can be considered as a equivalent solenoid. Okay, so I told you in the previous classes that only current can giving magnetism. If there is a current, definitely, if there is a magnetic field, definitely a current will associate with that. Okay, could you get that point? If there is a magnetic field, definitely there will be a current associated with that. So if there is a earth is producing magnetic field means there is a current. Did you remembering that idea regarding in the previous class? I have already communicated to you. Okay, so do you remember what is the current in which is producing earth magnetic field? Do you remember? Do you remember that? Do you remember? Then put it in the chat box. Let me see. Okay, so here a bar magnet will produce magnetic field. So what is the, if there is a magnetic field, there will be a current associated with that. What is the current? I told you in the last class, I will be explaining this idea because we have a topic in this chapter. So this is the topic. What is the current in a bar magnet which is producing magnetic field there? Let's see. So here there is a slices of magnet. Consider each slices. Okay, so let's see the cross section of a magnet, and for explaining it simply, I have taken it in a cylindrical form. Okay, so in the magnetic material there will be atoms, and in atoms electrons are revolving around the nucleus. So electrons are revolving. This is the direction of moving of electron. Only the valence electrons are represented here. Okay, so electrons are revolving means motion of electrons will be there. and that motion of electrons will be creating circular current. That motion of electrons creating circular current, and if you see, means you can see that here it's adjacent pair, this electron moving in the downward direction, and for this it is in the upward direction. So this will cancel, there will be cancelling effect. Since they are in opposite, the net effect will be zero. For all the adjacent pair, all the adjacent pair will cancel out. All the adjacent pair will cancel out. So what happened on the surface? On the outer layer, you can see that there is no cancel for the outermost or the electrons or the atoms near the surface. Only this will, I will take it with another color. Okay, that will be better. Okay, so this will, there is no cancellation for the surface electron. There is no cancellation for this kind of surface electron. So in overall, there will be a surface current. There will be a surface current. Okay, so consider a small thin slice of a bar magnet. So it will be creating a surface current. Another next, adjacent to that, there will be another slice, and for that, another current is there. Next slice, another current is there. Only surface current will be there. Okay, only surface current will be exist in a bar magnet. Okay, now we can see the solenoid. What is happening with solenoid? So if you are keeping these turns of the solenoid together, in each turn there is a surface, there is a current on the outer line, right? So similarly, you can consider these slices as a each turn of a solenoid. These slices as each turn of a solenoid. So in solenoid, what is current carrying solenoid? It is a bar magnet, and each slice is having surface current. Each slice is having surface current. Okay, so actually that surface current is producing magnetism in bar magnets. That surface current is producing magnetism in bar magnet. Is that easy? Is that easy? So look at the resemblance with a current carrying solenoid and a bar magnet. In current carrying solenoid, on each turn, there are current. Similarly, so we can consider a bar magnet for each different slices, thin slices. For every slices, there will be surface current through the edge of that slices. So, which means there is a surface current. Another slice, there is a surface current. For next, adjacent to that, the different slices will be there, and for each slices, there will be current in the outermost. Okay, there will be current in the outermost, and that have cute resemblance with a current carrying solenoid. So current carry, we know that current carrying solenoid will act as a bar magnet, right? So a bar magnet having that current kind of surface current, so which have cute resemblance. So that is why a bar magnet has an equivalent solenoid. Easy, right? Okay, so it is a very easy topic. Only how you can explain this heading, bar magnet as an equivalent solenoid. You can draw this diagram and also give the necessary points which need to be explained. This, so also you should mention the current in atoms, and outermost shell is represented here. So adjacent, this kind of adjacent current will cancel each other, and only there will be surface current, and that surface current is producing magnetism, and it will be having very much resemblance with a current carrying solenoid. This is what we have explained in this topic. Okay, easy. Okay, let's move to the next topic, and it's the last topic of this chapter: classification of magnetic material. Okay, so related to magnetic materials only, we have one more subtopic in this chapter, which is temperature dependence of magnetic materials. Okay, so classification of magnetic materials. Okay, in this chapter, we are discussing three types of magnetic material: diamagnetic material, paramagnetic material, and ferromagnetic material. Maybe you are familiar with these terms because in the lower grades, also with grade 10 and grade 11, we are dealing with this kind of terms, and only at grade 12 we are explaining what is this material, what's the nature and properties of this material. Okay, so you are familiar with this term: diamagnetic, paramagnetic, and ferromagnetic. In chemistry too, there are some terms that is comes in grade 12 chemistry, which is related to diamagnetism, paramagnetism, and ferromagnetism. Okay, let's have a look into this. Okay, so in this topic, we will be learning what is a diamagnetic material and what are the properties of that material. What is a paramagnetic material and what is the properties, and what is ferromagnetic and what are those properties of ferromagnetic material. Okay, so there are, I think, 8 or 9 property that you have to learn from for this topic. And for that, each material have different property. But if you learn one among, okay, let's take paramagnetic. So if you are learned properties of paramagnetic material, you can, it is very easy to learn properties of diamagnetic and ferromagnetic. How it is possible means, just give the same properties of paramagnetic material to ferromagnetic material, but given a dominant manner. If ferromagnetic material experience will move from weaker to stronger part of a magnetic field, same thing is happening with ferromagnetic material, but that movement will be very quick. That is what I said. The dominance of properties of ferromagnetic material will be more over paramagnetic. They have same properties, but ferromagnetic material exhibit same property with dominant manner. High dominance will be there. And what about diamagnetic material? The properties of diamagnetic material are just opposite to that of paramagnetic material. So how can you remember all the properties? Just learn the paramagnetic materials property and express that in high dominant manner for ferromagnetic, and express those properties in the opposite manner for diamagnetic material. So it will be easy. Let's see how we can represent. Okay, so we can move into diamagnetic material first. Okay, diamagnetic materials are those substance which produce develops feeble magnetism. What is meant by feeble magnetism? Feeble magnetism means small magnetism in the opposite direction of the given magnetic field. So when we place a diamagnetic material in a external magnetic field, they will develop small magnetism in the opposite direction. They will opposite. Diamagnetic material will oppose the given external magnetic field. So they will develop feeble small magnetism in the opposite direction of given magnetic field. Okay, so they will move from stronger to weaker part, which means if you are putting that diamagnetic material in a magnetic field, they will, since they are oppositely magnified, they will move from stronger to weaker part of that external magnetic field. Since they are oppositely magnetized, they will move from stronger to weaker part of the given external magnetic field. Example for those kind of materials are bismuth, copper, lead, zinc, tin, gold, silicon, nitrogen at STP, as well as water and sodium chloride. Sodium chloride is common salt. Okay, so there are different examples: bismuth, copper, lead, zinc, tin, gold, silicon, nitrogen at STP. What is STP? STP means, yeah, it is standard temperature and pressure. Okay, those who are very much good in chemistry will be understand what is STP. Okay, so bismuth, copper, lead, zinc, tin, gold, silicon, nitrogen, water, NaCl are the example for diamagnetic material. No need to remembering all the examples. You can remember 4 or 5. Okay, that's only needed. But you should remember at least 4. You should remember at least 4. Okay, what are the example for diamagnetic material? Okay, so they will magnetize in the opposite direction. Feeble magnetization in the opposite direction. Okay, let's see. This is the definition for diamagnetic material. Let's see what are the different properties. Okay, so the definition itself being the first property. So they will develop feeble magnetization in the opposite direction. They will develop feeble magnetization in the opposite direction. Okay, so what is meant by opposite directional magnetization? Let's see. Let's have a look. Okay, for that, to understand it clearly, let's consider a bar magnet. Okay, so regarding, imagine that this is a north pole of a bar magnet and south pole is there. Okay, so the south pole, definitely south pole will be also there. And I have taken, this was the pen. Yes, I have taken a iron nail and it will attract it, right? An iron nail will attract with a bar magnet. An iron nail will attract with that bar magnet. Okay, so if it is attracted by that magnet, what happened? If it is attracted by that magnet, what happened? What will happen? This, what will be the polarity of this nail, iron nail? Whether it is north pole for this and whether it is north pole or south pole. You know that if it is magnetized, if this iron nail is magnetized, it will be a south pole because we have given north pole to that. Okay, so since you have attached north pole of a bar magnet to here, the this end of the iron nail will magnetize and south pole will be here and north pole will be here. So this is same directional magnetization, in the same magnetize in the same direction. So don't think that magnetize in the same direction means for the iron nail it should be north pole. This is opposite direction. North pole is opposite, inducing north pole for this end is opposite directional magnetization. Here it is magnetized with a polarity south pole on the top, and it is said to be same directional magnetization. Okay, so here for a diamagnetic material, they will magnetize in the opposite direction, right? So opposite, let's see what is mean by opposite directional magnetization. Okay, for that, consider, okay, so I have taken two bar magnet, and this is the south pole of this bar magnet, right? This is south pole, sorry. Yes, this is south pole and this is north pole of this bar magnet. Okay, so how will the magnetization happen for diamagnetic material? So here it is opposite directional magnetization, right? Opposite directional magnetization means this is same directional magnetization. So opposite direction means it will be south pole. Don't think that these are same polarity, south pole and south pole. Don't think that these are same directional magnetization. This is just opposite direction. This is the opposite directional magnetization, and this will develop north pole. Here means it will be, since it is oppositely magnetized, north pole will be there. It will be inducing north pole here. Don't think that it is get it as a magnet. The magnet as like iron nail behaves as a magnet when it's attached to a bar magnet. South pole will be there, and this is same directional. This is same directional. Okay, same directional magnetization. This is what is opposite directional magnetization. Don't think that this is south pole and here it is also south pole. Don't think that this is magnetization in the same direction. This is magnetization in the opposite direction. Okay, so only south pole can induce north pole. That is what is meant by same directional magnetization. Here it is south pole is inducing south pole here, so it will be, it is for a diamagnetic material and it is what is said to be opposite directional magnetization. Okay, clear? Okay, so second point, in a magnetic field poles are induced on in a direction opposite to that of a inducing field. So this bar magnet are the inducing field and this material is diamagnetic, so they are oppositely magnetized, south pole here and north pole here. Okay, so what happened? Definitely there will be magnetic field starting from here, north pole to south pole. So there will be magnetic field starting from north pole to south. This is the direction of magnetic field, and there are several magnetic field be there. Since it is oppositely magnetized, all the field lines have preferred to passing through the air. Prefer to passing through the air. Okay, not through the magnetic diamagnetic material. They will prefer to passing through the air. For a diamagnetic material, the external field line passing through the air, prefer to passing through the air than going through the magnetic material. And I will give you a clear picture. So this is the picture. So this will be, since it is this is the origin of magnetic field, it will be north pole and this will be south pole of the external magnetic field. This will be the direction. From north to south there will be magnetic field, external magnetic field. Okay, so since the diamagnetic material is oppositely magnetized, all the field external magnetic field lines of force will prefer to pass through the surrounding air than going through the diamagnetic material, because diamagnetic materials are oppositely magnetized. Okay, oppositely magnetized, so the field lines are preferred to passing through the surrounding air. So this is the diagram that I have explained here. Since it is oppositely magnetized, the field lines prefer to passing through the surrounding air than going through the material. Okay, clear? Is that clear? Okay, so the lines of force get expelled or repelled. They are getting expelled, right? So this is the actual path. This is the actual path. But since, sorry, since there is diamagnetic material, they will repel the magnetic fields of force, or they will expel the magnetic field lines of force. That's why the field lines are preferred to passing through surrounding air. Okay, easy. Okay, then properties. The susceptibility of diamagnetic material is small and negative, sorry, is small and negative. Susceptibility, magnetic susceptibility of diamagnetic material is small and negative. Is small and negative. Okay. So when a rod of diamagnetic material is suspended freely in a uniform magnetic field, it aligns itself perpendicular to the magnetic field, which means okay. So imagine there is a diamagnetic material placed in a, sorry, this is south pole, right? South in a external magnetic field. What happened? What happened? So imagine that this is a diamagnetic material placed in a magnetic field. So what happened means whatever be the position we have placed this diamagnetic material, it itself align perpendicular to the external magnetic field. It will align perpendicular. So what is mean means, what does this means? Okay, so there will be from north to south pole there will be magnetic field, right? And this diamagnetic material aligned perpendicular to the magnetic field means if it is aligned like this angle will be 90 degree. The alignment of diamagnetic material and the angle between external magnetic field will be 90 degree. It will align perpendicular to the external magnetic field. So when we keep the diamagnetic material in external magnetic field, it will align itself perpendicular to the external magnetic field. Okay. Then the phenomenon of perfect diamagnetism in superconductor is known as Meissner effect and is beyond our scope of our syllabus, and we will not discuss in detail regarding that. Okay, so just remember phenomenon of perfect diamagnetism observed in diamagnetic material, sorry, in superconductors is known as Meissner effect. The phenomenon of perfect diamagnetism that is observed in superconductors is known as Meissner effect, and it is beyond our scope, and so that will be discussed not in detail. Okay, so the magnetization of a diamagnetic substance lasts so long as the magnetizing field is applied, which mean, so if you have placed a diamagnetic material, if you have placed a diamagnetic material, imagine that there is a diamagnetic material placed in an external magnetic field. This will be south pole, sorry, this will be south pole and this will be north pole. Okay, so if we place a diamagnetic material in an external magnetic field, so when we withdraw this magnetic field, the moment after that this diamagnetic material loses its magnetization, loses its magnetic properties. Okay, so when we withdraw the external magnetic field, when we remove this bar magnet, this diamagnetic material will turn into a normal material. Okay, there will be no induction of north and south pole in that material. Okay, its magnetic property will be losses the moment after we withdraw the external magnetic field. Okay, so that's the meaning of last statement. The magnetization of a diamagnetic substance lasts so long as the magnetizing field is applied. Okay, so it can exhibit magnetic properties till we apply the external magnetic field. Okay, so it will have the magnetic properties of, and as long as we are applying external magnetic field. Okay, so that's the meaning of last point. Okay, then we have to move to the next classification, paramagnetic materials. Okay, as I told you, we can take just opposite properties of diamagnetic material for paramagnetic material. Take it just opposite. So opposite means, here you can see definition. It will develop feeble magnetism. For diamagnetic materials also it is feeble magnetism, but for diamagnetic material they will develop the opposite direction. Here it is same direction. So when we place a paramagnetic material in an external magnetic field, it will develop feeble magnetization, which means small magnetization in the same direction. The previous one, it is opposite direction. Here it is same direction of the applied magnetic field or the external magnetic field. Okay, so when a paramagnetic material is placed in an external magnetic field, it will develop feeble magnetization in the same direction. Diamagnetic material will develop feeble magnetization in the opposite direction. Okay, here it is same direction. That's the difference. Okay, so they will be attracted by the magnet. In the previous case, it is repelled. In the case of diamagnetic material, it is repelled. Here it is attracted. That's why I told take in the opposite manner. Okay, here it is just opposite, reverse, right? Okay, so feebly attracted by the magnets and tend to move from weaker to stronger. In the previous case, it is stronger to weaker. Here it is weaker to stronger. Okay, so in the reverse order. Okay, so it is moved from weaker to stronger part of a magnetic field. Okay, example for paramagnetic materials are manganese, aluminium, chromium, platinum, sodium, and oxygen at STP. STP means standard temperature and pressure. STP means standard temperature and pressure. So, manganese, aluminium, chromium, platinum, sodium, oxygen are the example for paramagnetic material. Okay, so are the different example for paramagnetic material. So, paramagnetic material will develop feeble magnetization in the same direction of the applied field, and they will moving from weaker to stronger part. Weaker to stronger part of the applied field. Okay, so these are the this may be taken as the definition for paramagnetic material. Okay, let's see the properties. So the as I told you, we can take the first very first definition as the first property. Okay, so in an external magnetic field, they develop feeble magnetization in the same direction. They will develop feeble magnetization in the same direction. Okay, when they placed in a magnetic field, the lines of force prefer to pass through the material itself than through the surrounding air, which means okay. Okay, imagine that we have placed a paramagnetic material in an external field, external magnetic field. Okay, so as in the definition, they will develop feeble magnetization in the same direction. Same direction means south pole. Here it is south pole. It is oppositely magnetized. Here, if you have the south pole of a bar magnet, and here, if it is induced, south pole means it is oppositely magnetized. Okay, don't think that this is south and this is south. Same. It's not like that. Same means it should induce north pole here. It should induce north pole here. So, same direction. So, north pole here, and here it is north pole. So, it will be south pole. So, this is the same directional magnetization. Magnetization developed in the same direction. Okay, so they will form magnetization, feeble magnetization in same direction. So north pole here and south pole here. And if it is like that, what happened to the field lines? What happened to the external field lines of force? In the previous case, they are repelled, right? So here it should be attracted. The previous case for diamagnetic material, they are repelled, and for here it should be attracted. The field lines should be attracted. Okay, so let's see the diagram. So if you are placing a paramagnetic material in an external field, it will get attracted. So all the field lines get attracted towards the bar magnet. Sorry, not bar magnet. Attracted towards the paramagnetic material. Okay, they will attracted towards the paramagnetic material, which means the lines of force prefer to passing through the material, prefer to passing through the paramagnetic material than going through the surrounding air. So when we place a paramagnetic material in a magnetic field, the magnetic field lines of force will prefer to passing through the paramagnetic material than through the surrounding air. Okay. So the lines of force get slightly more concentrated inside the material, not then inside the material. Okay. Okay, inside the material. So, which means the concentration of field lines will be more inside the material compared to the surrounding air. So, when we place a paramagnetic material in a magnetic field, the concentration of field lines will be more inside the material when we comparing with the surrounding air. Okay, so the lines of force will be more concentrated in the material, inside the material. The lines of force will be more concentrated inside the material. Okay. Okay, can I move to this? Yes, next property. When a rod of paramagnetic material is freely suspended in a uniform magnetic field, what happened? It aligned itself parallel. Here, in the previous case, it is perpendicular. Sorry. Previous case. Sorry. My ink was black, that's why it's not visible. Okay, so now it is white. Okay, so in the previous case, it is aligned perpendicular. For diamagnetic material, they will align in perpendicular direction. Here it is parallel. Okay, so what happening is when we are having a paramagnetic material placed in an external magnetic field, so what is happening there? Okay, so when we are having a paramagnetic material placed in an external field, they will align itself parallel. It will align parallel to the external magnetic field, not perpendicular. It is perpendicular, right? It will align parallel. It will align parallel. Okay, so it will align parallel to the external magnetic field. External magnetic field. Okay, then paramagnetic material develop small magnetization in the direction of same direction of magnetic field, magnetizing field. We have seen that definition. Why here written over here again means it is develops small magnetization, right? Feeble magnetization. So the susceptibility will be small. Susceptibility will be small, and in the same direction, it is developed in the same direction. So it is positive. So paramagnetic material develop feeble magnetization in the same direction. So its susceptibility will be small and positive. What about diamagnetic material? It is small because diamagnetic material also developing feeble magnetization. So it is also small. But for diamagnetic material, they are developing in the opposite direction. Magnetization is developed in the opposite direction. So it is negative. Here, magnetization is developed in the same direction. So it is positive. So what is the significance of susceptibility? Here we can answer by looking at the value of susceptibility. We can say whether the material is paramagnetic or diamagnetic, as well as ferromagnetic too. Once we reach ferromagnetic material, I will explain the. Okay, so we if we have the value of susceptibility of a material, we can say whether the material is paramagnetic, whether it is diamagnetic, whether it is ferromagnetic. Okay, so if it is negative and small, it will be if susceptibility is like symbol for, do you remember what is symbol for susceptibility? It is chi. Okay, if chi is equal to 0.005, negative 0.005, susceptibility doesn't have any unit. Okay, so susceptibility is negative 0.005. What is that? What will be the material? What will be the material? It will be whether it is paramagnetic. No. If it is plus 0.005, it will be paramagnetic, because for a paramagnetic material, susceptibility is positive and small. Such susceptibility is small and positive. So by looking into the value of susceptibility, magnetic susceptibility, we can say whether it is para, dia or ferro. Okay, so as soon as the magnetizing field is removed, paramagnetic substance loses its magnetization. So same in the case of diamagnetic substance too. So diamagnetic substance get 1 second. So for a diamagnetic substance loses its magnetic property when we remove the external magnetic field. So here also for paramagnetic material, when we remove the external magnetic field, the paramagnetic material will lose its magnetic properties. Okay, so this is not like a just ordinary physics class. In actually, what we have done in previous chapters for grade 12 physics, we have lots of derivation. We have lots of equations. So here it will be only just like a lecture, as we are going for biology classes, right? So it's actually it is a relaxation chapter for you. There is no derivation. There is no that's kind of definition and all for this particular chapter. Only some points like just like properties, nature, behavior will be there. Okay, so that's a peculiarity of this chapter in grade 12 physics. Okay, so we can move to the next properties. Okay, not property, next last material, ferromagnetic material. So here also when we place a ferromagnetic material in a external magnetic field, what happen means they will magnetize strongly, not feebly, they will magnetize strongly. So they will develop strong magnetization in the same direction. Okay, so a ferromagnetic material will develop strong magnetization in the same direction of the applied field. Okay, so such substance are strongly attracted. Here also it is strongly attracted. In the previous case, for paramagnetic material, they are just attracted. Here it is strongly attracted. And in the first case, for diamagnetic material, they are repelled. Here instead of attraction, there will be repulsion. Okay, that's why I told. For if you are learning the properties of a paramagnetic material, you can take just reverse the properties of paramagnetic material so that it will be the property of diamagnetic material, and you can take the same property with property of paramagnetic material, and in a dominant manner it will be the property of ferromagnetic material. So that's why it is strongly attracted and strong magnetization and in the same direction. Okay, so such substances are strongly attracted by magnets and tend to move from weaker to stronger parts quickly. They will be quickly moving from weaker to stronger part. But in the case paramagnetic material, there will be it will be moving from weaker to stronger part, but not quickly. And what about diamagnetic material? They will move from stronger to weaker. Here it is moving from weaker to stronger. Okay, so example for ferromagnetic materials are iron, cobalt, nickel, and alloys like alnico. And being alnico is a ferromagnetic material, that's why alnico is used for making permanent bar magnet, not only bar magnet, permanent magnets. Okay, artificial magnet. Okay, so aluminum means alloy of aluminum, nickel, chromium, etc. Okay, not chromium, cobalt, aluminum, nickel, cobalt. Okay, so example for ferromagnetic materials are iron, cobalt, nickel, and alloys like alnico. Actually, aluminium is a paramagnetic material. Aluminium is a paramagnetic material, but nickel and cobalt is a ferromagnetic material. Okay, so they will develop strong magnetization in the same direction. Ferromagnetic materials are those substances which develop strong magnetization in the same direction. And example for ferromagnetic materials are iron, nickel, cobalt, iron, nickel, cobalt, alnico, iron, nickel, cobalt, alnico. Example for ferromagnetic materials are iron, nickel, cobalt, alnico, iron, nickel, cobalt, alnico. Okay, alnico is an alloy. Okay, okay. So here ferromagnetic substance exhibit properties like those of paramagnetic substance, but in a highly dominant manner. That's what I said. Ferromagnetic material exhibit same properties of paramagnetic material, but in a highly dominant manner. That's why I said you can learn properties of a paramagnetic material and take it in a dominant manner, highly dominant manner. It will be the properties of ferromagnetic material, and take the properties of paramagnetic material, just reverse it. It will be the properties of diamagnetic material. So that's the trick. Okay, so you need to learn about only one property, means properties of one object. You can take it highly dominant, it will be the property of ferromagnetic material. Just reverse it, it will be the property of diamagnetic material. Okay, so in an external magnetic field, this is a definition itself. So in an external magnetic field, a ferromagnetic substance develops strong magnetization in the same direction. Develops strong magnetization in the same direction. Okay, so we can take external magnetic field, south pole here and north pole here. Okay, so when we place a ferromagnetic material, a ferromagnetic, we can color it, right? Yes, we can give the color yellow. Okay, so imagine there is a ferromagnetic material. Okay, so they will magnetize in the same direction. Same direction means what? Same direction means south pole here, so it should be north pole. North pole here, it will be south pole. That is what is same directional magnetization. Okay, so it will develop magnetization in the same direction, and it will be strong enough. This ferromagnetic material will be strongly magnetized. That's why if you are taking a bar magnet and an iron nail, it will strongly attracted by it. That's why strong magnetization. If you are taken a bar magnet and an aluminium, you can take an aluminium sheet or any plates that is having in the kitchen, and if you have got nearby it, if you have taken that bar magnet near to that aluminium material, they will attract but not strong enough. But for an iron, they will strongly attracted because aluminium is a paramagnetic material, and magnetization, development of magnetization in that particular material is not strong enough. It is feeble only. But here, for an iron being iron is a ferromagnetic material, they will develop magnetization in the strong manner, highly dominant manner. That's why it is strongly attracted. Okay, did you get that point? Okay, so they will develop magnetization in the same direction in the strong manner. Okay, so properties. Then, if you have placed a ferromagnetic material in an external magnetic field, what is happening? It will develop magnetic field within that ferromagnetic material. So if it is north pole, definitely, sorry, if it is if it is if it is north pole, it will develop south pole here. If it is south pole, it will develop north pole here. Okay, so development of magnetic field in the same direction, and so that it is strongly magnetized, the field lines of force have a tendency to go through the material. Same that is happening with paramagnetic material too, but here it is the tendency of field lines to attract it towards the ferromagnetic material is more. So here the tendency of field lines to attract it towards the ferromagnetic material will be more. Okay, so by seeing the behavior of field lines, by seeing the behavior of field lines in a by seeing the behavior of field lines in an external magnetic field, we can predict whether the material is diamagnetic, paramagnetic, or ferromagnetic. Okay, so how can we predict? So here, before going to that, the lines of force get more concentrated inside the material than comparing with the surrounding area. So the field lines of force will prefer to passing through the material, and the lines of force will be more concentrated inside the material comparing to the surrounding air. So as I said, how can we classify or how can we understand which material is represented by this diagram? We can simply look into the behavior of magnetic field lines. Okay, so here whether the field lines are attracted or repelled. Here, for in this case, whether the field lines are attracted or repelled. Here it is repelled, right? So obviously it will be diamagnetic material. Obviously it will be a diamagnetic material. Okay, so here you can see that for these two cases, the field lines are attracted. All the field lines are in the two cases, field lines are attracted towards the material. The field lines are more concentrated inside the material compared with the surrounding air. So, but if you simply look into means, it's understood that here it is more attracted or more concentrated comparing with this one. So here the development of magnetization is strong. So strong means it will be a ferromagnetic material and it should be paramagnetic. Okay, so by simply knowing the behavior of magnetic field lines, we can understood that, or we will be able to understood that whether the material is diamagnetic, paramagnetic, or ferromagnetic. Okay, easy, right? Yes. The remaining properties of ferromagnetic material: when a rod of a ferromagnetic material is suspended freely in a uniform magnetic field, it will quickly aligns. Sorry, or should be changed. Okay, it will quickly align. It will quickly align itself parallel. In the case of paramagnetic material, it is also aligned parallel. It's also aligned parallel to the magnetic field, but here it is quickly aligns. Okay, so let's see what is happening. So when we placed, okay, so when you have placed a ferromagnetic material in an external magnetic field, so it will align. Align. How will it align? It will align quickly parallel to the external magnetic field. It will align parallel to the external magnetic field. Okay, not perpendicular. This is perpendicular alignment. And it will align parallel to the external magnetic field. Okay. Yes. Then a ferromagnetic material develop large magnetization. A ferromagnetic material develop large magnetization in the in the same direction. Okay, so I have shown it here because this is being the definition, but from this definition we can create the susceptibility. How look like the susceptibility of ferromagnetic material? Since they develop large magnetization, the susceptibility is also large, and since it is in the same direction, it is positive. Okay, so in the previous case it is small and positive, small and positive. Here it is large and positive. For paramagnetic material, it is small and positive. For ferro, it is large and positive, and for dia, it is small and negative. What is negative and what is the small? Susceptibility, magnetic susceptibility, chi. Sorry, yes, chi. Magnetic susceptibility, chi, is small and negative for diamagnetic, and small and positive for paramagnetic, large and positive for ferromagnetic material. That's why I said learn the properties of a paramagnetic material, just reverse it, it will be the properties of diamagnetic. Just take it in dominant manner, highly dominant manner, it will be the properties of ferromagnetic material. Okay, easy, right? Then it retains magnetism even after the magnetizing field is removed. So it is only the property of ferromagnetic material. So when we take an iron nail and when we got attracted towards a bar magnet, when we remove that bar magnet, it can retain that magnetic properties for a small time. That is what is meant by retains magnetism even after magnetizing field is removed. When we remove the bar magnet, the iron nail can have that magnetic properties for a small time because iron is a ferromagnetic material. Okay, okay. So these are the different properties of ferromagnetic material. Okay, so as I said, you can learn the properties of a paramagnetic material, just reverse it, you will be the properties of diamagnetic material. And just learn the properties of paramagnetic and take it in the highly dominant manner, it will be the properties of ferromagnetic material. Okay, you see, that is a trick. That is the only trick that how you can learn all those properties. Okay, last topic of this today's chapter, temperature dependence of last topic of today class, temperature dependence of magnetic properties. Okay, for that, let's see Curie's law. Okay, so Curie's law says that the intensity of magnetization of a paramagnetic material, intensity of magnetization is denoted by the letter M. Okay, so intensity of magnetization, or simply magnetization or magnetization intensity. So intensity of magnetization of a paramagnetic material is directly proportional to magnetizing field intensity, which is denoted by the letter H. So M is proportional to H. So intensity of M is proportional to H. Intensity of magnetization of a paramagnetic material. Paramagnetic only for paramagnetic. Okay. So Curie's law describe about intensity of magnetization of paramagnetic material. So it is directly proportional to magnetizing field intensity H, and M is inversely proportional to absolute temperature. Absolute temperature means temperature which is taken in Kelvin scale. Okay, so it's not, don't confuse with absolute temperature. It's just temperature taken in Kelvin scale. Okay, Kelvin is SI unit of temperature, not degree Celsius. Okay, so M is proportional to H and M is inversely proportional to 1 by T, which implies I can write it together. M is proportional to H by T. Or M should be equal to, which implies M should be equal to some constant into H by T. Some constant into H by T, and this constant C is known as Curie's constant. Curie constant. Okay, so that constant C is known as Curie's constant, and from this equation we can write what is M by C. What is M divided by C? What is M divided by C? M divided by C will be equal to H by T. M divided by C is equal to H by T, which is again is equal to chi. What is chi? What is chi? Do you remember what is chi? Do you remember what is chi? Chi is the magnetic susceptibility. Chi is the magnetic susceptibility. Okay, so chi is the magnetic susceptibility. Okay, so from this equation, what can I write? Yes. I got chi is equal to H divided by T. Magnetic susceptibility is equal to H divided by T. What is T? Absolute temperature. Or I can say that for a paramagnetic material, magnetic susceptibility is inversely proportional to absolute temperature. So Curie's law states that magnetic susceptibility of a paramagnetic material is inversely proportional to absolute temperature. Okay, so as temperature increases, the susceptibility of a paramagnetic material decreases. That's why inversely proportional. As temperature increases, susceptibility of a paramagnetic material decreases. So this is the behavior of paramagnetic material with temperature, or this is the dependence of temperature on magnetic properties of a paramagnetic material. Its susceptibility decreases with temperature. Magnetic susceptibility of a paramagnetic material decreases with temperature. Okay, then modified Curie's law or Curie-Weiss law. What is that? It is given the effect of temperature on magnetic properties of ferromagnetic material. Ferromagnetic material. Let's read the statement. The susceptibility of a ferromagnetic substance above Curie temperature is inversely proportional to the excess temperature above Curie temperature. Lots of confusions are there. Curie temperature, above Curie temperature, like that. Okay. So what is meant by Curie temperature? Curie temperature is denoted by letter Tc. What is that Tc? T subscript C. Curie temperature means when we have heated up a ferromagnetic material, at a high temperature, this ferromagnetic material will turn into paramagnetism or paramagnetic material. The ferromagnetic material at high temperature will having properties of paramagnetic material, or ferromagnetic material will turn into a paramagnetic material. So Curie temperature is that temperature in which that ferromagnetic material is turning to paramagnetic. So when we heated up a ferromagnetic material, the ferromagnetic material will turn into a paramagnetic material. So that temperature in which this transition occurs is known as Curie temperature, denoted by the letter Tc. Okay, so the susceptibility of ferromagnetic substance above that Curie temperature or Tc is inversely proportional to the excess temperature above Curie temperature. What is meant by excess temperature above Curie temperature? So you can see Tc is the Curie temperature, and if I have heated up to a temperature T, then what is T minus Tc? What is T minus Tc? What is T minus Tc? Suppose imagine that 800 Kelvin is the Tc, Curie temperature of a particular material, and I have heated up that material up to temperature T is equal to 1000 Kelvin. Okay, what is T minus Tc here? 1000 minus 800, which is equal to 200 Kelvin. So this is the T minus Tc. T minus Tc, it is the excess temperature over Curie temperature, right? This 200, when we heated up a temperature of 1000 Kelvin, this 200 is the excess temperature of this over this Curie temperature. So what did this Curie-Weiss law says is that the susceptibility of a ferromagnetic material, susceptibility of a ferromagnetic material is inversely proportional to excess temperature over Curie temperature. Excess temperature over Curie temperature. Susceptibility is inversely proportional to excess temperature over Curie temperature, which means when we have increased the temperature above Curie temperature, what happened? Its ferromagnetic properties decreases, or susceptibility decreases. So when this excess temperature over Curie temperature increases, or when we have heated above Curie temperature, what happened? Its susceptibility, magnetic properties like susceptibility will decreases. Okay, so they are inversely proportional. The ferromagnetic material, when it is heated up, it will turn into a paramagnetic material. Okay, so I can write chi is equal to some constant and I call it as C dash divided by T minus Tc, and this is what is our modified Curie's law or Curie-Weiss law. Okay, so this is what is known as modified Curie's law or modified Curie's law or Curie-Weiss law. Okay, so chi is equal to C dash divided by T minus Dc, where C dash is a constant. So this is the temperature dependence of magnetic properties of a ferromagnetic material. Okay, so we have discussed the temperature dependence of magnetic properties of paramagnetic material, and same for ferromagnetic material. What about diamagnetic material? Actually, the magnetic properties of a diamagnetic material is independent of temperature. It does not depend on, sorry, it does not depend on temperature. Magnetization of a diamagnetic material does not depend on temperature. Okay, so in this class we have discussed the current loop. How will be the polarity of a current carrying loop, and how will be the polarity, and thereafter we have look how a bar magnet is equivalent to a current carrying solenoid. Then we have discussed what are the different magnetic material and the properties of each, and how the magnetic properties of that material depend on temperature. Okay, so these are the topics that we have discussed for today's class. Okay, and we have completed this chapter 2. Okay, is there any doubts? Please put it in the comment box. Let me see. Okay, so on 8th of November, this Wednesday, coming Wednesday, the Amala ma'am from the Department of Biology, Goscore Learning, will come up with chapter 5 of grade 12 biology, molecular basis of inheritance, and it's part 2 video. Okay, so please stay tuned and happy learning. Thank you.